Dear student, welcome to the first lecture for sampling. We will begin with a simple random sampling. Simple random sampling is a method for collecting n units of about n, such as every one of the n combination small n samples has an equal chance of being drawn. In practice, a simple random sample is drawn unit by unit. The units in the population of the neighborhood from 1 up to capital N. A series of random numbers between n and capital N is then drawn, either by means of table or random numbers or by means of computer program that produce such as table. At any drawn, the process of used you must give an equal chance of selection to any number in the population not already drawn. The units that have been these n small numbers constitute the sample. It's easy to verify that n combination n samples has an equal chance of being selected by this method. Consider one definite sample that is one of set small n specified units, and the first draw of the probability that some of the n small specified units is selected n over n. At the second draw, the probability that can be one of the remaining n minus 1 specified unit is drawn n minus 1 over capital N minus 1, and so on. Hence, the probability that all n specified units are selected in n small n draw is small n over capital M multiplied by n minus 1 over n minus 1 times n minus 2 over n minus 2 up to 1 over capital N minus small n plus 1. This means that n factorial times n minus n factorial over capital N factorial, which is equal to 1 over n combination n. Since a number that has been drawn is removed from all the population for all subsequent draws, the method is also called random sampling without replacement. Random sample without replacement is entirely feasible. At any draw, all the capital N members of the population are given an equal chance of being drawn, no matter how often they have already been drawn. The formula for the various and estimated variances of estimates made of the sample are often simplified when sampling is with replacement than when the formula for the variances and estimated variances of estimates made from the sample are often similar when the sampling is with the replacement than when it is without replacement. For this reason, sampling with replacement is sometimes used in more complex sampling plans. Although at first sight there seems little point in having the same unit two or more times in the sample. In sample survey, we decide on certain properties that we attempt to measure and record for every unit that comes into the sample. These properties of the units are referred to as characteristics, or more simply as items. The value obtained from any specific item in the unit n capital N units that comprise the population are denoted by y1, y2 up to y capital N. The corresponding values for the units in sample are denoted by y1, y2 up to y small n. Or if we were to refer to a typical sample member by of I1, 2 up to small n. Note that the sample will not consist of the first n units in the population except in the instant, usually rare, in which these units happen to be drawn. If this point is kept in mind, my experience has been that no confusion needs result. Capital letter refer to the characteristic of population and lowercase letter is those of the sample. For totals and means that we have for the following definitions. As mentioned in the table, we have the formula for population and sample for the total and the mean. And then, although sampling is undertaken for many purposes and interests, centers most frequently on four characteristics of the population. First one is mean, which is noted by y per. For example, the average number of children per school. The second is the total, which is equal to capital Y. For example, the total number of arcs of the width in the region. 3. Ratio of two totals or means, which is denoted by capital R, equal to capital Y over capital X or Y par over YX. For example, the ratio of liquid assets to the total assets in group of families. Finally, the proportion of the units that fall into some defined classes. For example, proportion of the people with false teeth. Estimation of the first three quantities is discussed in this chapter. The sample height, denoted as estimate of a population characteristic made from a sample. In this chapter, you have the simplest estimator of the are considered. We use this table for y par population mean, y the total population, and r which is the population ratio. And the formula given in this table is like this. In y hat, the factor capital N over N by which the sample total is multiplied is sometimes called the expansion or raising or inflation factor. The inverse small n over capital N, the ratio of the size of the sample to the population, is called the sampling fraction, or it is denoted by log F. As we have seen, a method of estimation is unbiased if the average value of the estimate taken over all possible samples of a given size small m is exactly equal to the true population value. If the method is to be unbiased without qualifications, this result must hold for any population of finite values, yi, and for any m. To investigate whether y par is unbiased with simple random sampling, we calculate the values of y par for all n capital combination in small samples and find the average of the estimates. The symbol E denoted the average over all the possible samples. Now we will take the 2.1, which is the sample mean y par is unbiased estimate of y par. Prove this by definition. The expected value for y par equal to summation y par over n combination n. Summation y par equal to summation y1 plus y2, y3 up to yn over n combination n equal to n small times factorial capital N over n small factorial times n minus n factorial, where the sum extends over all n combination n samples. To evaluate the sum, we find out how many samples are any specific value yi appears, since there are n-1 other units available for the rest of samples and n-1 other places to fill in the sample. The number of samples continuing up to yi is n-1 combination n-1. So, hence, summation of y1, y2 up to yn equal to n capital minus 1 factorial over n minus 1 factorial times n capital minus n factorial times y1, y2 up to yn. From the previous equation, we find that expectation y par equal to y1 n minus 1 factorial times over n minus 1 factorial times n minus n times n factorial over n minus n factorial times y1, y2 up to yn. Here, if we eliminate the values with each other, we get y1 plus y2 up to yn over capital N, which is equal to y bar. So we can take a corollary from this theorem, which is y hat equal to n capital times y bar is an unbiased estimate for the population total y. Alice compares some proof of theorem to one is obtained as follows. Since every unit appears in the same number of samples, it's clear that expectation y1, y2 up to yn must be some multiple of y1, y2 up to yn. The multiplier n minus over n, since the expression on the left has n terms and that on the right has capital N terms. This leads to the same result for the proof of the previous example or previous slide. Thank you for listening, and we'll continue in the next pages.